Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Dear student, Assalamu alaikum. My name is Dr. Muslim Khan, Assistant Professor, Department of Chemistry, KUST. Today, the topic of our discussion is hyphenated techniques focusing on LCMS, liquid chromatography mass spectrometer. The course code is CHEM453 in a course mass spectrometric and thermal method of analysis. As you know that we have already discussed HPLC, high performance liquid chromatography, just to refresh your knowledge. What is the principle of LCMS? LCMS is a technique that combines the physical separation capability of HPLC and analysis power of a mass spectrometer. So LCMS is the hybrid technique, is the combined technique that combine the physical separation capability of HPLC and analysis power of a mass spectrometer. It is the method that combines separation power of HPLC with detection power of mass spectrometer. One of the most important property of HPLC that it separates the different component of the mixture very well, while the mass spectrometer act as a excellent detector because you can easily do the quantitative and qualitative analysis by a mass spectrometer. So in LCMS, what we do, we remove the detector of HPLC. As we have discussed that HPLC have a different types of detector like refractive index detector, like UV detector. So we remove that detector, and when the eluent is coming from the HPLC, instead of going it into a detector of HPLC, it goes into the MS from the column by interface to the MS. So it means that in between HPLC and MS, there is an interface. So in most cases, the interface used in LCMS are the ionization source, basically. So HPLC is a method of separating complex mixture into its components. High sensitivity of mass spectrometry give information about the identification and structure information of analyte. So combining these two important characteristics of these two important techniques, so HPLC plus MS, we are getting LCMS. As the analyte elute at the end of LC enter into the MS where it is ionized. This is the system components of LCMS, how it looks like. So this is the compartment of HPLC, high performance liquid chromatography devices. You know, we have discussed already that there is a solvent system and HPLC system, and then here is a degasser, And then there is a sample compartment. After sample compartment, this is basically the mobile phase coming along with sample coming from here. It is split. Some of it is going into the waste. This is a waste, and the rest is going into the column. So after the column and HPLC, here is a detector, but we remove this detector, not completely remove, we make it off. Then the eluent is coming to the mass spectrometer. So here is an interface plus ion source. So interface plus ion source. Then that is going to the mass spectrometer, wherein first it is ionized. You already know the principle of a mass spectrometer. So where it is first ionized, and then in a mass analyzer, it is separated on the base of mass to charge ratio, and then ions are detected. Then we are getting the spectra. So from LCMS, what we get actually, at the end, we get a chromatogram. Because chromatogram we are getting from HPLC, and chromatogram, and we are also getting a spectra. So we get both information. So the components are separated. For each component, we are getting spectra in a mass spectrometer. But combining LC with MS, we have some problems. Like, first of all, we will discuss the HPLC. The HPLC is working at a this is the liquid phase operation. While this is working at a temperature of in between 25 and 50 Celsius degree, and there is a no mass limitation for HPLC. It requires inorganic buffer, and they required a flow of gas like 1 ml per minute. While on the other hand, MS is working at a very low pressure, means at a vacuum operation, because the ions you can't dictate ions, you can't working with ions at atmospheric pressure. So vacuum operation is needed for this MS. So working at a temperature of 200 to 300 degrees Celsius, while the mass limitation 4000 Dalton for quadrupole mass analyzer, and it require organic volatile buffer, while a gas flow of even 10 ml per minute is working with MS. So there is a massive difference between these two techniques. This is working at atmospheric pressure, this is at. So combining these two was a difficult job to do, although this one is having its own plus point and this one is having its own plus point, but the combining was a problem. So interface was needed. So when something coming from here, so that it goes there, so that it reach a detector. So first of all, the mobile phase in chromatography, because the first part of LCMS is chromatography. So this mobile phase is basically carrying the sample with it to the column, and then where it is separated, and then into the mass spectrometer. So this, the requirement of the mobile phase, it must be a low cost and also having a high purity, because it will increase in the background noise uh, for the uh, for for the analysis. Also, it must have a low viscosity, and also it must be a non-toxic and a non-flammable. And the other thing is that it must be non-corrosive to the LCMS system component. Also, the HPLC column is the heart of the chromatographic system. So the column is one of the most important component of HPLC chromatograph. We already discussed in HPLC, because the separation of the sample component is achieved when these components pass through the column. The high-performance liquid chromatography apparatus is made out of stainless steel tubes with a diameter of 3 to 5 millimeter and length ranging from 10 to 30 centimeter. Normally, columns are filled with silica gel, we have already discussed, because its particle shape, surface properties, and pore structure help to get a good separation. Silica is wetted by nearly every potential mobile phase, is inert to most of the compound, not reacting with those compound, has a high surface activity which can be modified easily with water and other agents. Silica can be used to separate a wide variety of chemical compound. Its chromatographic behavior is generally predictable and reproducible. This is how the chromatographic column look like. So this is made of a stainless steel. Inside that stainless steel, the packing material is basically filled. So there are fast column, and those are usually short column, usually 15 to 50 millimeter. And there are micro column, LC column, long column, and those are 20 to in between 150 millimeter. So, but for chromatographic system, uh, you have to prepare. So for this LCMS system, you have to prepare the sample. The sample preparation usually we have discussed is you have to concentrate the analyte so that it is easily detected while removing the material which can cause interference, which can cause problems. So the basic purpose is to how to get the analyte and how to remove the unwanted material from it. So first of all, pre-concentration is one of the method which you can use. We have discussed this pre-concentration. That pre-concentration means what is the initial volume, and you have to redissolve in a final volume that must be very less, so that if you are having, let's say, you are having 10 ppb analyte in your sample. So if the initial volume is 100 ml, and at the end you dissolve it in 1 ml, that is 100 times pre-concentration, means 10 ppb multiplied by 100, so it make it, I think, 10 ppm. So this is pre-concentration. And desalting, usually if the sodium is present, if potassium is present, it is making then sodium adduct in a mass spectrometer, because this is LCMS system, and usually it is making a potassium adduct. We have discussed it in a mass spectra that there will be an ion in a mass spectra, M plus 23 ion, M plus 39 ion. You remember it. So you have to desalt your sample. And the third one is the filtration to remove lower molecular weight drug. These are the common few techniques used in a sample preparation. Filtration is used to remove low molecular drug from protein, plasma, and milk. So the next one is interface. So how you are connecting basically HPLC system with the MS system. An LCMS system, if LC is directly connected to the MS system, the liquid phase would vaporize and resulting in a large amount of gas being introduced to the MS system. So when a large amount of gas is introduced into the MS system directly, so what will it result? It decrease the vacuum level, because we have mentioned it that a mass spectrometer working at a very low, means at a vacuum level. So stop the ions to reach the detector. So when the vacuum level is decreased, so it will be very difficult for the ions to reach to the MS detector. So interface is basically needed. What types of interface are there? It is difficult to interface liquid chromatography to the MS because the necessity to remove the solvent as I told you, that when the solvent is introduced into the MS system, that will vaporize and too much gas will be created there, and then the pressure of then the vacuum level will be disturbed, and it will be very difficult for the ions to reach to the detector. So the most common interfaces are, so basically electrospray ionizations, because you have already you have already studied electrospray ionization in a mass spectrometry. That what does electrospray ionization do? Electrospray, first of all, it sprays. We will discuss it. It sprays the your solvent, and solvent is evaporated. Eventually you are getting ions, so it means that this is basically working is interface for for mass spectrometry. And the second one is thermospray ionizations. By heating you are doing you are evaporating your solvent. And the other one is atmospheric pressure chemical ionization, and the fourth one is atmospheric pressure photoionization. Is Are the types of interfaces used in the LCMS system. First of all, what is electrospray ionization? Just to refresh your knowledge, solution passed through a capillary at a high potential produce a mist of highly charged droplets. We already discussed electrospray ionization in detail in a mass spectrometry. So solution passed through a capillary at a high potential produces a mist of highly charged droplets, and these pass down a potential and pressure gradients, and droplet reduced in size by evaporation, Coulomb explosion, and the result is fully desolvated ions. These ions result from a complete evaporation of the solvent or field desorption from a charged droplets. So this is how these droplets are created at a very high potential, and then the Coulomb, then evaporation of solvent, and then eventually a Coulombic. So evaporation droplet, there are three steps basically in this: droplet formation, droplet shrinkage, getting smaller and smaller, and gaseous ion formation. And you know there are two models to explain that how ions are created here in this electrospray ionization. You know that very well. One is charge residue model, another one is electron is ion evaporation model. Second one is thermo-ionization source. Basically, there are two types. One is this real TSP thermal ionization source. Another one is this discharge electrode for external ionization and repeller electrode. The only difference is that here in this one, this repeller electrode is fitted. So basically, what we are doing, we are heating this sample. We are having this EI filament. We are heating coming from HPLC EI filament. So the electrons are basically bombarded, and here heater. So basically we are going, what we are doing, we are evaporating the sample. We are evaporating the solvent from the sample. So the next one is atmospheric pressure chemical ionization. So gas phase ions molecular reaction at atmospheric pressure, and this is similar to chemical ionization but working at atmospheric pressure. Primary ions produced by corona discharge and a solvent spray, suitable for polar and non-polar molecules. Just to refresh your knowledge, because we have discussed that in mass spectrometry, and usually gives monocharge ions, so typically used for a molecule less than 1500 Dalton. So this is the diagram of EPCI source. And electrons for primary ionization are not produced by heated filament because it would burn out atmospheric pressure. Thus, the corona discharge is used, which is fairly insensitive to corrosive or oxidizing gases. Corona discharge, a luminous discharge, we have already discussed this thing as well. A luminous discharge from the surface of an object that is highly charged electrically, created at atmospheric pressure by applying high voltage pulses between two electrodes. generate a large flux of energetic electron, which can then be used to initiate or enhance a variety of chemical, biological, and physical processes. This is the more detailed view of the mechanism of the EPCI. So you can see here, this is the HPLC inlet system. This is coming here. So this is a coronal discharge, and this one is then doing ionization in for the mass spectrometry. This work is an interface for mass spectrometry. Strength of EPCI, so advantage much more efficient in ionization, at least 1,000-fold. And why ionization take place at atmospheric pressure, leading to a high collision frequency. That's why it is more efficient. And it is less thermal decomposition because of the rapid dissolution and evaporization of the droplets. And very efficient ionization source specifically for LCMS system, because it can work as an interface as well, and suitable for a range of analyte polarities. And the next one is atmospheric pressure photoionization. This is similar to chemical ionization, but instead of corona discharge here, a UV lamp is basically used. This is another a very suitable interface ionization source for LCMS system. And vaporizer convert the LC, this vaporizer convert LC eluents to the gas phase, similar to the EPCI. Photons from discharge lamp ionize the analyte molecule. These photons, instead of corona discharge, ionize the analyte molecule, particularly good for non-polar compound lipids and for low LC flow rates. And then once these ions are created after the interface in the ionization source, then these ions are basically separated on the basis of charge, mass to charge ratio. There are different mass analyzers used in LCMS system, but specifically quadrupole, time of flight, and ion trap mass analyzer are used in a LCMS system. So we have discussed what is quadrupole mass analyzer, what is time of flight, and what is ion trap mass analyzer. So I don't want to waste my time, or because we have already discussed in very detail all these mass analyzer and a mass spectrometry. So at last, what are the application of LCMS system? LCMS system have a very wide application nowadays, like in pharmaceutical application. So you can do a rapid chromatography of different drugs you are preparing, identification of different drugs you are preparing, you are using. So rapid, for example, rapid chromatography of benzodiazepines, identification of bile acid metabolites. So these are the pharmaceutical application. It is also having a biochemical application, rapid protein identification, using capillary LCMS, MS, and database searching. Also, it is having a clinical application, high sensitivity detection of trimipramine and thyroidazines. It is also having a food application, like identification of aflatoxins in food, identification of different toxins in food, and determination of vitamins and D3 and poultry feed supplements. Environment, it is also having a environmental application, detection of phenylurea herbicides, detection of low level of carbonyl in food, and also having a forensic application, illegal substances, toxic agent, explosive, etc. These are the application of LCMS system. Uh, so these are here are some books: JD Questions, Coogee and West, Dog Laws, and these are the different books you can use for this lecture. And thank you very much.